Thank you, Francesca, and good morning all. So I have prepared a set of slides in order to provide, let's say, a high-level overview of what our group provides could sustain as technological solutions, with an emphasis on the Unibo marketplace offerings, because the name is a bit exotic and let's say blotted with some technical terminology. Now, as a group, we are very active in research and development in what it's called this continuum of verticals and technologies, which are the focus of the so-called Industrial IoT Consortium. But this project puts an emphasis on the manufacturing domain. And by the way, even though we are an academic group, let's say more oriented towards implementing proof of concept solutions, our solutions, a big subset of those have been tested and are tested in operational environments. So let's talk about TRL 6, TRL 7. Now, I've chosen to focus on a very specific, let's say, subfield or a research area, which is that of data analytics, and also provide some examples of actual tools, open source tools, which we adopt and have developed through various European projects. So this is to discuss a bit about the traditional architecture for the so-called big data platforms. So on the left side of this figure, we have the various sources of information, which, by the way, they may be heterogeneous. And these data sources are connected to this other conceptual layer, which is called conceptual layer in this figure, the data collection layer in this figure, via various connectors. The important thing in here is that data get homogenized, so the various connectors which interconnect with the specific data sources, they perform some syntactical or semantic transformation. Data are stored in a homogenized fashion in a NoSQL or in a relational database. Then afterwards, you have the other layers whereby you perform some aggregation on these already stored values, and then you feed this aggregation or even the raw data themselves into analytic tools whereby you train these predictive models or artificial intelligence model which serve a purpose. The thing in here is that in this traditional way of computing data, the decisions are made after the fact. So we call about this paradigm is also referred to as data at rest. Now, there is another paradigm, which is called streaming analytics or native streaming, whereby you process a single piece of data the moment it enters your system. So in here, you generally talk about publish-subscribe systems, like let's say Apache Kafka might be an example, NATS is yet another example, and both of these are open source products used by big companies. Think of Facebook, think of Google, think of Netflix, LinkedIn, and so on and so forth. You do this in order to decouple the components and gain in scalability. So other, let's say, non-functional requirements you need to have, and these are desirable. So with streaming, we go towards another paradigm, which is called data in motion. In motion, you can analyze data the moment they are generated and enter your system. So you can analyze when the fact actually occurs. Now, with actual platforms, production-ready platforms, so what in reality you need is a mix of these approaches. So a mix between the data in rest and data in motion. You use historical data to perform some computation and gain some information and knowledge about the, let's say, physical phenomena you are monitoring or you try to mimic. And you use this prediction to perform, let's say, some anomaly detection for the data that enters your system in real time. Now, between these components, now the interactions become quite complex, and there are several paths. You configure them on a per need basis. So the idea of these, let's say, mixed worlds is to enable prediction on a piece of data the moment the data arrives in your system. Now, inside several European projects, and specifically inside this Innovation Action Project, we have beyond TRL7, let's say, a platform as a service, which implements and helps to manage and control this hybrid and distributed digital twin concept. So the idea in here is that you have intelligence, you can have some concept of intelligence at the thing, being the sensor that monitors an event. But you can deploy that intelligence, a more complex intelligence, in some edge node, which is deployed on premise to your company. Then you also rely on the cloud to perform some more compute-hungry computations. So you can use the cloud to control all your assets. You use the edge to control a subset of those assets, but you can also have intelligence and control the thing itself. This intelligence is acquired by exploiting the data. And by the way, in this project, we have several test beds related to manufacturing, to predictive maintenance. Think of aiming to perform predictive maintenance of a smart grid which is geographically distributed. You can deploy some lightweight predictive capabilities at the thing itself. Think of a small wind turbine. You can deploy an intelligence which controls some functionalities pertaining to a field comprised of wind turbines, and use the cloud to control all your assets, the entire smart grid. The cloud is involved in training these heavy models. These heavy models can be synthesized and deployed at the edge, controlling a subset of the assets. So the wind turbines, it can be also deployed on board the wind turbine. I think of a Raspberry Pi also. And these entities, there is model synthesization involved from the cloud towards the thing, and the thing is connected and feeds data to actually improve these models. Now, talking about, let's say, a tool which has a more reduced scope. This is an open source project from the Linux Foundation, and it's the de facto industrial IoT platform out there. So this is by default cloud native, and by cloud native I mean it has a microservice oriented architecture and a pluggable architecture. All these components, all these layers are containerized entities. They can be deployed also as VMs, which are more power hungry, and they can be orchestrated, controlled, and coordinated toward the common goal. So the classical scenario is that you have a plant floor with things that talk in different languages, being that REST, OPC UA, Modbus, or whatever other sort of protocol. It is available out there, or it can be developed via the software development kit this platform provides. So you have things which feed data at this core service layer. Data are homogenized, they can be stored at the edge. They can be further processed. Think of an anomaly detection tool. You want to identify whether you've received any data which the logic considers as an outlier data, but they can also be exported in a raw format, so the piecewise data or an aggregate of the data, towards the upstream, whereby the upstream can identify an edge node or the cloud. So there are already developed connectors, and we have developed some in-house, which integrate this platform with other, let's say, IoT platforms. Think of Amazon, think of Google, think of IBM, where you can do, let's say, more compute-hungry sort of computations. Okay, so this is all I had prepared, just to give a brief overview on what those items are. And if you are interested to go into further details and to assess whether these solutions could help you in your use case, you're welcome to do so. This is my contact, and I guess the presentation will be made available to you afterwards.